Our next speaker is Dr. Ralph Mead, Professor of Chemistry and Biochemistry at the University of North Carolina, Wilmington. He received his PhD in chemistry from Florida International University in 2003. He was the 2017-2018 UNCW Distinguished Scholar Award recipient. He's an associate editor for the journals Marine Chemistry and Estuarine Coastal and Shelf Science. And he's been honored as a member of the James Merritt $1 Million Club with a total external funding of greater than $3.5 million.
All right. Thank you very much, Martin. Enunciate. Yes, sir. Oh, so the camera. Okay, fair enough. All right, just give me a second here. And then advance. Gotcha. Cool. All right. Thank you I just want to say thank you to the conveners for giving me a chance to come up here and show some of the research that myself, my colleagues, and most importantly, the grad students and postdocs are performing in the lab, because Lord knows I don't make it in the lab as much as I would like to, so the results I show are theirs and not mine. So I am a professor of chemistry here, and I thought instead of jumping right into results, and since we have such a broad base of folks here, I figured since I teach for a living, I would talk a little bit about what it really means, this idea of mass spectrometry, and focus it more so on the environmental aspects, which is what we're here for. So without further ado, let's go ahead and start. So 25 minutes? Okay. All right, so what I have up on the screen here, and pardon me if I get close to the board here, this is how I like to teach. So these three images are posed with the question, why mass spectrometry for environmental research? All right, so it was a great segue into this slide from Larry's talk, where he brought up this idea of an NMR. An NMR is a great tool, but it's got to be much like having a tool chest in your garage. You have to have the right tool for whatever sort of question that you pose or something that you have to fix, right? So with that in mind, I just want to point out a couple things for what MS, and that's how I'm going to refer to it as, is MS. When an MS is coupled to a chromatographic system, such as a GC or an LC, and keeping in mind that the chromatographic system will separate a complex mixture in time. So you hope that you have peaks, purified peaks, that go into the MS. And once that takes place, the MS can, one, act as a means to detect, right? So it will tell you, as the analyst or the chemist, when a peak is a peak, right? The advantage of this, of having the MS, is that the mass spectrometer has much more selectivity and sensitivity compared to many other analytical detectors, which, as chemists, we have in our toolbox. And just a side note to that, as time has gone on, the field of mass spectrometry has been around for quite some time, but it's only been the past few years where the speed of scan speed and the electronics have really caught up, where now you can have benchtop, high-powered MSs with the sensitivity that allows us to do what we're doing with the Gen X, that is, detect ultra-trace concentrations in a very complex mixture or matrix, such as the Cape Fear itself. Okay, so I've talked to you guys about how the MS can act as a way to detect a peak. The added part of that, in which this is where MS really shines, is that you get a mass spectrum that goes along with it. So what I have here, basically, I know it's a little pixelated, and I apologize for that. But what I have here is a chromatographic peak, and with the software, when you click on that peak, and ideally it's pure, underneath, wherever you use the software, you will have a mass spectrum that goes along with that peak. So that mass spectrum then, for the most part, is a unique identifier for that purified compound. All right. So over on your right and the right side up top, I have two examples of this. The first is hexane, right? And then underneath is ethylbenzene. Each of these, of course, are organic compounds. They're, of course, not to Gen X, but I put them up here to show you that the individual mass spectrum for each is a unique identifier. So if you had an unknown, then you can use this to hopefully piece back together what that organic compound is. Closer. All right, I will use the arrow. There you go. All right, fair enough. Okay, so quickly, basically to summarize what I said, in the underlying part there, the basic idea of an MS is to generate ions and separate them by their mass to charge, that is M over Z. We, as chemists or scientists, can use that info, like I said, to determine whether you have a detection of a peak or any sort of structural information. All right, this is the analytical side of my brain. I am an analytical chemist, and I love to open up the black box, and I hope you guys will enjoy this as much. I'll briefly, this is just a schematic of a typical ion trap, and it's a type of MS. We have various parts here. We have our source, which puts the charge onto the organic compound. And the key thing is here, if you cannot put charge on the organic compound, then you have an overpriced paperweight. So the source is a really important part of the whole thing here. And then we have a series of ion optics that go to our mass spectrometer, which in this case is an ion trap. One thing I want to point out is all of this is under a high vacuum, 10 to the minus 7 torr. Depending on the type of MS you have, it can be 10 to the minus 10 torr. The whole idea behind this is whatever decompositions that ensue, you want them to be unimolecular, that is, as a result of not bumping into anything else. So that's why we pump it down and get rid of as much air as we can and have a long Mead-free path. Okay. All right, so I want to point this out here. In the news, in the discussions that I've had, I know I've seen, there's a lot of discussion about this idea of low and high resolution MS. MSs are not NMRs. For those of you who have seen an NMR, it's just a can. It's not just a can, but it's a can that if I have an NMR in my lab, you have one in your lab, and for the most part, they're the same thing. In a mass spectrometer, not necessarily. I like to think of them as an island. Each of the islands do certain things. So up top here, I have, this is from our laboratory, I have what's called an ion trap. This is a low resolution MS. We use it to quantify with. So we know what organic compound we want. We have a standard for it. We go ahead and separate that out chromatographically, and we record that peak. It's great for the things that you know that you want. Right here I have what's called the quadruple time of flight. All right, they're both blue, that kind of gray, but their job is completely both ends. They're two separate lands. The one underneath here takes advantage of this idea of high resolution, where given infinite resolving power, there's only one molecular formula that can apply to any M over Z. And that is what the bottom MS is used for, is to go after those unknowns. All right, so the next thing I wanted to point out was this idea that it takes time to do Gen X, PFAS, any of these emerging contaminants. It's not like the crime shows where the officer walks in with the white stuff and it gives it to the chemist puts it in a machine and out spits whatever it may be within a short amount of time. It doesn't work like that. So I just wanted to quickly point this out and not go in depth, but to show you the steps that are involved just for the PFAS. And if you count them off, 1, 2, 3, 4, 5, 6, and 7 steps, just to get the sample extract onto the MS. That does not count the analyst, the student, my time to go through and figure out what we have there and quantify. So it takes time. And always, as y'all move ahead, keep this in the back of your mind. This is research, and just so happens that this part of it, it's not fast. All right, so switching gears. So I've given you, hopefully anyway, a little bit more of an appreciation as to what it takes for the MS side of things, what sort of sample processing is involved. Now I'm going to switch gears and talk a little bit about the sedimentary distribution in the Cape Fear, as well as some atmospheric research my colleagues and I have done in regards to Gen X and a few of the other perfluorinated compounds. All right, so let me give the lay of the land here. All right, so here we have, of course, a map, and I've got highlighted pins here of the middle Cape Fear. And basically, if you start at Station 4, which is at the very top here, this is above Lock and Dam 3, above the Kumur site. The Kumur site I have right here. Site 3 is the William O. Husk Dam. Then moving down, we have Lock and Dam 2 at Site 2 or Station 2. And Station 1 is our closer to home here at Lock and Dam 1. All right. Our sampling efforts have been in response where the university was asked to participate in House Bill 56, which I'm sure you all know about. Part of our group's efforts has been to understand the spatial, that is up and down the Cape Fear at a multitude of sites, and the temporal, that is with time. Sedimentary concentration of the Gen X. The concentrations that I show here are from just one of the transects, and you see that we have up until now collected 4 of the transects. Larry said this, and this is true, for the sedimentary analysis of these replacements like the Gen X, there was not a method for us to work off of, so we had to develop one in-house. Took a little bit of time, actually quite a bit of time, but based upon a performance-based metrics, we are able to fully recover 100% our surrogates, which we spike in, so we have confidence in our results. And so from one of the transects, we have from Site 4 going down to Lock and Dam 1 here, a concentration in nanograms per gram dry weight of sediment that looks like this. Now this is just one of the transects. Our students, myself, my colleagues in the summer will complete this, the rest of the transect that we have here. Let's move on now to the lower part of the Cape Fear. And this is more closer to home. People ask me this a lot. Well, Why do we even go past Lock and Dam 1? Well, because we're scientists. We are curious. This is why we've gone past it, because there are implications with long range transport of sedimentary bounded Gen X. Okay? All right, so again, the same or similar type map where the pins show each of our sites. Up until now, we've only gotten through one of these. Again, similar transects and dates, again, with the idea to get the spatial and temporal variability. Our site M61 is a part of the Lower Cape Fear program, same site that Mike and Larry use. And it's close to the downtown area here. And you notice that we have one concentration here from one of our sites at 14 nanograms per gram dry weight. Okay. Yes, sir. Right, yeah, good point. So everybody's been having a very good lesson on the parts per. This is ppb, or parts per billion. The caveat to this is you cannot equate this parts per because it's mass to mass. And so don't equate this to a drinking water health advisory that's mass to volume. All right, that's an important point. All right, so the significance of what we have so far. Gen X, as defined by our cast there, has been detected in our sediments to date. This data, along with our additional measurements, such as percent OC, grain size, will help us understand the environmental fate of this organic compound. And last but not least, this is one of the more, or in my opinion, one of the more important parts. The sediments act as an integrator of processes in the water, right? So you can almost think of it as a long-term reservoir. The question has to be posed, well, if Gen X, say, is in the sediments, is there potential for long-term release into the overlying water even though the point source has been cut off? Okay. Switching gears just a bit. With the analytical workup and extraction for Gen X, we get a whole slew of the other perfluorinated compounds, okay? What I have shown here is what's called an extracted ion chromatogram, where x-axis is time, y is response. This is from our high resolution quadruple time of flight. And the reason we use this QTOF is only two of these, well, three now, but at the time did not have standards for all of these. I have obtained through a custom synthesis PFMOAA. Dr. Striner at EPA has shared with me the Nathions, and of course there is Gen X here. My point that I want to make with this is that you can count off the Roman numerals of each of the peaks, 1, 2, 3, 4, 5, 6, 7, and 8, and 6 of them have reported in the peer-reviewed literature tentative structures where a standard was not available. So of course, peak 1, PFMOAA, this is Nathion 2, peak 5, which is this guy here, and then of course Gen X, peak 4 here. But of interest are peaks number 7 and 8, the larger peaks of the group. These are unknowns that have not been reported, at least in the Cape Fear as far as I can tell, based upon the mass deficiency, based upon the high resolution MS work and their isotopic distribution. These two compounds appear to be perfluorinated and have one atom of chlorine. All right. So what they are, that is what my group and I are trying to work on right now, and that involves a variety of techniques such as MS, things like that. All right, so switching gears yet again, and I'll wrap this up soon because I know I'm getting close on time here. Okay, my colleagues and I have had continuous National Science Foundation funding, or NSF, for a precipitation site here on campus for approximately 25 years. So when we saw this idea that the potential based upon the DEQ, DAQ stack emissions of GenX and a whole slew of other PFAS compounds, we all were like, we got to go and look at it in rain. That's how this came about. And this is a photo of our precipitation site at school. All right, so the first thing that we did is when we were looking at the emitted list, we discovered upon looking at this that there is this organic compound and also what others have referred to as hexafluoropropylene dimer acid fluoride. It's a mouthful, but the point that I want to make here is this. If you pull back, for those of you who have had organic chem, this functional group right here that hopefully you guys can see in the red dot here, where you have the carbonyl and the fluorine. This is an acyl fluoride or an acid fluoride. This is emitted in fairly large amounts from the Chemours stacks into the air. The question we had, and in discussions with others, is how quickly that will hydrolyze, that is, convert in the presence of water over to the carboxylic acid, which is what we typically detect and what we refer to as GenX. So we performed, well, okay, before I say that, I bought this. You can buy this pure, neat. I bought some, and we performed a quick F19 NMR experiment where you could follow the hydrolysis, that is the loss of this fluorine to, the conversion of that fluorine, that acyl fluoride group, into the carboxylic acid in a matter of minutes. In fact, it happened so fast that we added it to the NMR tube, and pretty much by the time we got it from our hand into the NMR, it was pretty much almost done. That is, the conversion took place so quick. So the take-home of this is that the dimer acid emitted into the atmosphere can rapidly turn into what we call the GenX, that is the carboxylic acid, when it encounters water. So it could be in rain, it could be a droplet in a cloud. And the key thing here is this, which I'll lead into my next talk, or my next point. It has the potential to be transported via atmospheric processes long range. All right. Okay, getting to the end here. All right, so this is where I start talking about a little bit of atmospheric research that my group and I, my colleagues and I are in. So the question is, how does wind direction impact GenX? That is the concentration that we find. All right, so what I have shown here, this plot and this plot, these are what's called these are a 36-hour hindcast. This is from high split, with HiCom, which is from NOAA. You all can gain access to these. You just need to know when the rain quit, and you can figure out where that air mass came from at multiple heights. Our site is right here, and what I have shown here is a rain event. This is just how we call our rain. We collect on an event-based basis. We do not, repeat, do not do a composite. And the reason we don't do that is because you lose critical information if you mix rain events, due to the fact that the air masses that contribute to that rain event do not come from the same place, all right? So, which is shown here. So what I have here now is a hindpass of this rain event that occurred November of last year. Gen X was below our LOD. We got 1/4 of an inch of rain. We didn't have enough to do the pH. But the point is, this air mass came from over the ocean. The next rain event, December 8th, you see now that our side is here, but now the air mass came from land. In fact, it came somewhat close from the Kumur site, and the concentration of the Gen X in this rain was well off our Cal curve. So the only thing I can tell you in terms of concentration was it's above our highest point. And we got quite a bit of rain here, almost like 2 inches of rain, and pretty typical pH. So the take home from this slide is that air mass, where that air comes from to contribute to the rain, has a big impact on the concentration of the Gen X and the long range transport. We're approximately, 100 miles or so from the Kumur site. So there's the possibility that this stuff can move. All right, so it's not last slide. All right, so just to wrap it up, I want to make these 3 points here. There are many questions that remain as to the environmental occurrence, transport, and fate of these replacement PFAS compounds. I'm not referring to the C8s, the PFOA, PFAS. Those are, there's been a lot of work done on that. There's a whole slew of new ones that have come out. One of the big things is, what do these things look like from an organic chemical point of view? In order to do that, it takes a lot of work. It takes a lot of MS work. It takes, if you can get enough material, NMR work, and in conjunction, the two can do the full structure elucidation, right? The other side of that is you need standards. A lot of these compounds, the concentrations are referenced back to, say, Gen X. We know, I see it, the response for all of these on the LC-MS are not the same, all right? So having structural confirmation will be important for other scientists involved, such as the toxicologists, the utilities, the regulators, so on and so forth, the folks here in this room.